Harmonic analysis. In this video, I will discuss about the harmonic analysis, what is that, and how to perform the harmonic analysis study using ETAP software. This video is going to be a large one, so I have decided to split this video into two parts. Here, firstly, I will show you how to start from the scratch and what are the impacts of the linear and non-linear loads, and also the limits, that voltage harmonic distortion limits and current harmonic distortion limits as per IEEE519. That thing also I will validate using the ETAP software. So this video is going to be in detail starting from the scratch, and at the end you will be able to understand how to perform that harmonic analysis in a power system network, and also what are the basic criteria and which points we need to emphasize. So let's start. Firstly, let me draw one very simple network which consists of one grid, next one bus, in between there is a cable, let's say this is 110 kV bus. Next, two winding transformer, okay, in between there is cable connection. This is secondary side transformer, secondary side 11 kV. Grounding, this is 30 DYN1 delta star transformer. So this is 11 kV bus. And now the cable size, let's say this is 50 meter from library this is 110 kV. Let's select this cable. Okay, so transformer rating, let's say this is 10 MV transformer. Impedance typical X by R I am using, though we should not use the typical X by R ratio or the transformer impedance. So what should be the cable size? Primary side current 52 amps. Let's say this is 10 meter from library. Okay, this secondary side cable 20 meter I am considering. 11 kb XLP 3 core 50 hertz 3 core 240, number of conductors per phase 3, impedance. Okay, so up to this, and now what I will do, I will assign one load here. Suppose this is static load. There is a cable MVA, let's say this is 3 MVA, power factor 100 percentage. Okay, and this cable size 20 meter. So I am starting from the scratch so that it will be helpful for the beginners as well, how to do that, how to perform from the beginning. So it will be very helpful for them. 95 square mm. Okay, so this is done. So in this simple system, what I have assigned, there is a grid, connection. This is a 110 kV bus. There is a step down transformer, 10 MVA transformer, 110 kV by 110 kV by 11 kV, and one static load I have modeled here. So it's a very simple network. For this network, let's run the load flow analysis first. For this load flow analysis, loading, nothing. Okay, these are okay. So simply we'll run the load flow analysis just to check what's the loading. Okay, cable to positive impedance 0. Okay, so we need single core. Okay, let's run the load flow analysis. Okay, now we can show the unit here, kV. So this is the power flow. If we see here, the voltage is voltage in percentage. There is a load connected here. Okay, let's do one more thing. Let's assign one HV circuit breaker here. ABB 12 630 amps. Okay, so first of all, let's open this breaker, and in this network only there is a grid, power source, 110 kV bus, one step down transformer of 10 MVA, and 11 kV bus. There is no load connected here. Now let's run the load flow analysis. So here the voltage is 100%. Here at 11 kV this voltage is also 100%. Okay, now if I close this and again I can simulate this one. So this load is connected. Now the voltage is down to 99.78%. And if you see the specialty here for this load, 11 kb load connected here, harmonic is not assigned. This is considered as purely linear load, 100% power factor, that is unity power factor, and harmonic is not assigned here. Now if we consider this load as the source of harmonic, what are the loads to be considered for the source of harmonic? Let me show you. This one is the UPS, this is BFD, battery charger, and this is inverter. So all these sources are the non non-linear loads, and these are the sources of harmonics in a power system network. So up to this, let's run the harmonic analysis here. Click here, and now this is bus 1, this is bus 3. We'll run this harmonic load analysis, but before that, let us check this briefcase study case editor. Here plot, I want to plot this, let's say bus 1 and also bus 3, because 11 kV this is bus 3 and 110 kV this is bus 1, and also the cables, all the cables I want to check the harmonic contents, the status here. So now if we run the harmonic analysis here, let's see what are the errors it is showing. Power grid 3-phase short circuit MVA, it is not defined. X by R ratio not defined. Positive sequence single phase, X by R ratio, zero sequence, negative sequence. So all are related to this grid. But when I am going to run that load flow analysis, simple load flow analysis here, if we run that load flow analysis, ETAP is not throwing any error because it is not required here. But whenever we are going to run this harmonic analysis, this grid or the source parameters are required to be defined. Why? Because if there is a if we want to perform that harmonic analysis, then the harmonic currents are flowing from the load side towards source side. Once again, I am repeating my statement. For the harmonic analysis study, the harmonic currents flows from the load terminals, that means the source of harmonic, towards the power source. It may be grid, it may be generator, or any other voltage or current source in the network. So for that reason, ETAP will ask you what will be the source impedance, what will be the source short circuit level, whether it is grid, whether it is generator. So what will be the source impedance and source X by R. So all these parameters are required to be defined. So that's why it is asking, and ETAP is throwing the error message. So let us define the grid source parameters here. It is considered as the swing bus here, on this rating 110 kV short circuit MVA. Here let's say this is X by R ratio, this is 15.5, and this short circuit level, let's say this is 40 kiloamps. So now this is the 7621.023 is the short circuit MVA, and accordingly this positive sequence resistance value and reactance value, these are defined here. So X by R ratio is 15.5, and the short circuit ratio, this short circuit current is 40 kiloamps. So this is now defined, and now we'll go to simulate the harmonic analysis here. So if we want to show the units here, show the units and all the branch circuits. Let's say this will be in percentage voltage. Okay, now this is the slider, harmonic analysis slider, and here you can see this is 0% THD, total harmonic distortion. This is 0% because this load, there is no source of harmonic. This is considered as a linear load, plain static load. There is no harmonic content here, so that's why 0% total harmonic distortion. And here also at 110 kV bus, this is also 0% THD. Okay, that's fine. Now if we assign this harmonic from the library, we can pick from the predefined preloaded library data, or we can create the library here. We can create the library here also. So for the time being, we are uh, using one ABB. This is ACS 6006 pulse, 6 pulse. We are using this one, and this is the waveform. And if we use, this is the 12 pulse, the waveform will be better than 6 pulse, like this. So for the time being, we are using this 6 pulse. Okay, now let's simulate this one. You can see this is 6.58% of total harmonic distortion it is showing. And here this is the branch circuit. First of all, this is the voltage harmonic. This 99.99% RMS. This is the percentage in RMS value voltage, and 6.58% is the total harmonic distortion. And here 44.35% total harmonic distortion. This is not voltage, this is the current harmonic. And here also at 110 kV bus, 0.101% total harmonic distortion, but the current harmonic is high, which is 44.37%. Now we can plot this. Let's say we are going to check this bus 3, and waveform and spectrum order. What we can say, this is the voltage waveform. This is the distorted voltage waveform of bus 3, that means 11 kV bus. This is waveform and this is the spectrum, and from this spectrum it is clear that the fifth order harmonic is of highest magnitude. This is the highest magnitude, fifth order harmonic, then seventh order harmonic. This is almost half of the fifth order harmonic, then 11th, 13, 17, 19, and so on. But the total harmonic distortion, which is 6.58%. So in this way we can check this one. Now the question will come whether this is acceptable or not. What IEEE 519 is saying about this harmonic content. What should be the limit, whether we should accept this 6.58% voltage harmonic THD, or and this current harmonics of 44.35% of total harmonic distortion, or there are individual harmonic content. Suppose this is fifth harmonic, this current distortion is 41.207%, and here also 41.221%. Whether it is acceptable or not, that will be driven by the IEEE 519 tables. In that IEEE 519 tables, it is clearly mentioned there what will be the limit for the voltage harmonics and what will be the acceptable limits for the individual current harmonics based on some other criteria. We will check that in the next video, which will be part 2 of this video. Before that, in this video, I would like to share one more thing here. Let's say this is the harmonic, this is the source of harmonic. If we plot another load, let's say another static load here, and cable and one breaker as well. Okay, let's say this is 2 MVA, 100% power factor, but there is no harmonic content here. Now if we open this breaker, that means we are connecting this linear load with a grid and one step down transformer. Let's see what will happen if we run the load flow analysis here. Okay, so cable length, we need to specify the cable, 20 meter. Let's select copper cable, record 95 impedance. Okay, fine. Now if we run the normal load flow analysis, yeah, it's fine. Now we'll go to the harmonic analysis here, and we will simulate this harmonic analysis. Okay, and before that we need to define this is what is the cable number. Okay, plot this all cables. Now run the harmonic analysis. Here you can see that is 0% THD. That means there is no harmonic distortion, there is no source of harmonic, that's why it is showing 0% THD. Okay, fine. Now if we close this, means if this is the load where the harmonic is included, 6 pulse waveform it is included. Let's see the previous condition, as we have already run this previously. This is 6.58% THD. Now I will close this breaker as well. Previously it was 6.58% and here 44.36% like this. Now let's run this. This is now reduced 6.29% of total harmonic distortion. Here also 25.96% of total harmonic distortion. Previously it was 44 point something. It is reduced. And one interesting point is that here if you see, this is 6.29% total harmonic distortion. Though this load is linear, there is no harmonic source of harmonic, then also 6.29% of total harmonic distortion it is showing. Why it is showing? Because if we see this bus 11 kV bus, plot bus 3, if we see this, the voltage appearing in this bus 3 11 kV bus, that itself is not purely sinusoidal wave. There is a this is the distorted waveform. So the existing available voltage waveform, it is already distorted. So that's why the load which is connected with this distorted waveform, with this distorted voltage 11 kV bus, that is also contributing the total harmonic distortion. That's why it is showing 6.29 percentage. So in this way we can check the cables as well. For the cable we can see all the cables, you can see the plot. Okay, so all the individual cables are showing here in this waveform, and this is the spectrum. Okay, now in the next video, part 2 video, I will validate using that IEEE 519 tables. I will show how to validate that value using ETAP software. So check out the part 2 video.